Have you ever wondered how the solar panels on rooftops, fields, and even satellites are made? Solar panels have become essential in our shift to renewable energy, powering everything from homes and businesses to remote scientific missions. But what exactly goes into making these incredible devices that can transform sunlight into usable electricity? Today, we're going behind the scenes to look at the entire journey of solar panels, from raw silicon to the finished products capturing the sun's power. Solar powers are a marvel of modern engineering, combining advanced materials, precise manufacturing, and rigorous quality control to create a clean, reliable energy source. Very quickly, please take a moment to support our channel by hitting that subscribe button, and don't forget to give this video a like by clicking that thumbs up button. Alright, let's jump right in. Solar panels play a powerful role in today's energy landscape, turning sunlight into electricity to help power our homes, workplaces, and even entire communities. But how do they actually work? At the core of solar panels' operation is a technology known as photovoltaic, or PV cells, which are designed to absorb sunlight and convert it directly into electricity. This conversion process is clean, quiet, and most importantly, renewable, meaning it doesn't produce any harmful emissions or rely on finite resources like fossil fuels. Solar power has become more important than ever as we work to reduce our carbon footprint and combat climate change. Because sunlight is abundant, especially in sunny regions, solar panels provide a sustainable way to generate power without straining the planet's resources. They're commonly installed on rooftops, solar farms, and even mobile setups for off-grid applications, demonstrating their versatility. With the demand for solar technology rising rapidly, innovations in solar panel design and efficiency are also accelerating. From city rooftops to rural fields, solar panels are now helping us build a cleaner and more sustainable future. But to really understand what makes these panels so impactful, let's dive into the fascinating process behind how they're made. To create a solar panel, the process starts with one of the most abundant materials on Earth, silicon. Although common, silicon in its natural state needs to undergo extensive purification before it's ready for use in solar cells. The process begins by extracting raw silicon from quartz or sand. This raw silicon is then purified in a high-temperature furnace, creating a highly pure form known as solar-grade silicon. Once the silicon's purified, it's melted down and formed into cylindrical ingots. These ingots are large, solid blocks of silicon that serve as the raw material for the next stage. However, these blocks are much too thick to use in solar cells as they are. The ingots are then sliced into ultra-thin wafers, each wafer measuring only a few hundred micrometers thick. Precision is crucial at this stage, as the thinner the wafer, the less silicon is used, which helps improve cost efficiency, yet it must be thick enough to absorb sunlight effectively. This wafer-thin silicon is the foundation of what will become a solar cell. Each wafer is carefully polished and inspected for impurities or imperfections. This process demands meticulous quality control, as even minor flaws can affect the efficiency of the final solar panel. These wafers now possess the structural properties needed to capture sunlight and convert it into electricity, making them an essential starting point in the journey to creating solar power. Once we have silicon wafers, they're ready for a crucial transformation that allows them to capture and convert sunlight into electricity. This step involves a process called doping, which alters the wafer's electrical properties by introducing tiny amounts of other elements, typically phosphorus and boron. These elements create what's known as a positive-negative junction within the wafer. This junction is essential for generating an electric field that will help separate and direct electrons when sunlight strikes the surface. After doping, the silicon wafers undergo an anti-reflective coating application. Silicon naturally reflects a significant amount of sunlight, which could reduce the panel's efficiency. To counter this, the wafers are coated with a thin, dark layer that minimizes reflection and increases sunlight absorption. The coated wafers now appear bluish-black, which is why solar panels often have a dark or blue hue. The final part of this stage involves layering the wafer with a metallic grid. This grid, often made from silver or aluminum, is carefully applied to the surface of the wafer, allowing it to conduct electricity once the sunlight activates the cell. The grid is designed to maximize efficiency, covering it just enough of the wafer's surface to capture the electric current without blocking too much sunlight. By the end of this treatment process, the silicon wafers are transformed into functional solar cells, ready to be linked together to harness sunlight and produce electricity. With the silicon wafers now transformed into fully functional solar cells, the next step is to assemble them into an interconnected system capable of generating significant power. Each cell by itself can only produce a small amount of electricity, so multiple cells are linked together to form a complete circuit. This process begins by arranging the cells in a precise grid pattern, often grouping 60 to 72 cells for residential and commercial panels. Once positioned, the cells are connected using conductive materials, typically metal strips made from highly conductive materials like copper or silver. These strips, known as bus bars, act as electrical highways that collect and transfer the electricity generated by each cell. The cells are soldered to the bus bars to ensure a solid conductive connection that can handle high currents. This interconnection is critical for ensuring that the solar panel can produce a stable and efficient flow of electricity. The assembled solar cells now function as a single unit, generating a steady electric current when exposed to sunlight. This current can be directed into an inverter to convert it from direct current, or DC, to the alternating current, AC, used in most homes and buildings. At this point, the cells are fully wired and configured as a complete functioning array. However, these delicate cells need protection from the elements to perform reliably, which brings us to the next step in the solar panel production process: layering and encasing the cells for durability. With the solar cells interconnected and ready, the next step is to assemble them into a sturdy, weather-resistant solar panel that can endure the outdoors for decades. The assembly process involves layering the solar cells between several protective materials to shield them from harsh environmental conditions, while ensuring they remain efficient over time. First, the interconnected solar cells are sandwiched between two sheets of encapsulant material, usually made of a durable plastic like EVA, or ethylene vinyl acetate. This encapsulant serves as a cushion, protecting the cells from moisture, dust, and impacts. Above the cells, a layer of tempered glass is added to shield them from external elements, while allowing maximum sunlight to pass through. This glass is specially designed to be shatter-resistant, protecting the cells from debris, hail, and other potential hazards without compromising efficiency. Beneath the cells, a sturdy backsheet layer is added. This layer, typically made of a strong polymer, prevents moisture and contaminants from penetrating the panel from behind. It also adds structural stability, keeping the panel rigid and durable. Finally, the entire assembly is framed with a metal, usually aluminum, which reinforces the panel and makes installation easier. The frame holds all the layers securely together and provides a mounting surface, making it easy to attach the panel to roofs, racks, or ground mounts. With these protective layers in place, the panel is ready for testing and quality control, ensuring it meets the standards required for reliable, long-term energy production. Before a solar panel can be installed and begin generating electricity, it must pass through rigorous testing and quality control processes. These tests ensure that the panel not only meets energy output standards, but can also withstand extreme weather conditions for many years. Each panel undergoes a series of simulated environmental tests, including exposure to high winds, heavy rain, snow loads, and intense heat, all designed to verify its durability and resilience. One of the most important tests is performance testing, where the panel's ability to generate electricity under controlled light conditions is assessed. Engineers measure the panel's efficiency to make sure it converts as much sunlight as possible into usable electricity. Panels that meet or exceed performance benchmarks move on to certification, ensuring they comply with industry standards and safety regulations. Additionally, each panel is inspected for physical flaws. Technicians check for cracks in the glass, frame imperfections, or issues in the electrical connections that could impact performance or longevity. Only after passing these strict tests is the panel certified and ready for installation. These quality checks are crucial, is they guarantee that the solar panel will provide a reliable, sustainable energy source capable of powering homes and businesses with minimal maintenance for decades to come. From purified silicon wafers to powerful, durable panels, the process of making solar panels is both complex and fascinating. Each step, from engineering to assembly to rigorous testing, ensures that solar panels can reliably capture the sun's energy and convert it into a clean power for decades. Solar technologies change the way we think about energy, opening up a world of sustainable possibilities. If you enjoyed learning about how solar panels are made, don't forget to subscribe for more insights into the world of renewable energy and innovative tech. And let us know in the comments, would you consider going solar in your home? We'll see you next time.